We're on the last section of Chapter 17, 17.7, Electrolysis. Here we're going to describe the process of electrolysis, compare the operation of electrolytic cells with that of galvanic cells, and perform stoichiometric calculations for electrolytic processes. So electrolysis is a process in which a non-spontaneous reaction is driven with the work of an external circuit. So for instance, recharging batteries, refining metal ores, commodity chemical manufacturing, electroplated metal coatings for things like jewelry, utensils, and auto parts. These are all examples of using electrolysis. So one example is the electrolysis of molten sodium chloride. So this is used to manufacture metallic sodium and chlorine gas with the use of what is called a Downs cell. So you take molten sodium chloride, literally so you have that in the liquid phase to produce the sodium and the chlorine gas. You have a positive potential that is greater than the negative potential that needs to be applied to the cell, because normally this reaction would not be spontaneous. You have to add some extra potential to the cell. Here's what it looks like. So you've got the blue here. This is not water. This is liquid sodium chloride. So this is using the Downs process. Usually uses iron cathodes and carbon anodes. And then you have some voltage source to make this process go. Then we have the electrolysis of water. I remember actually doing this experiment when I was a freshman in high school. We did a little electrolysis experiment. It was really cool. So this is done to decompose water into hydrogen and oxygen gases. The hydrogen ion concentration is often increased with the addition of a strong acid. And then to make this happen, though, you have to have a cell voltage that's greater than 1.229 volts that is applied to the system. So since the potential of the cell is negative 1.229, you need to be greater than the positive 1.229 to make it flow in the opposite direction. So when I did this in high school, we used a little battery. It was really cute. So this is an example of a water electrolysis setup to make your oxygen and hydrogen gases. So you have little collection sides for each of your gases, so they're separated. There's also electrolysis of aqueous sodium chloride. So this is part of the chlor-alkali process that's used by industry to make chlorine gas and sodium hydroxide, which is also known as lye. So sodium hydroxide or lye you can actually get at hardware stores. It is basically very, very strong drain cleaner. So if you have a clog in your drain that is from something like oil or, let's say someone poured like burger grease or something down the drain instead of throwing it away, and then it cools and it solidifies. Use sodium hydroxide, so go to the store, get some lye, pour it down your drain, or you can dissolve it in water first, pour it down, and it'll take care of your clog. There's two potential anode reactions that can happen. And then what ends up happening is in the system, you see that both these oxidation reactions are occurring. And then there's three possible cathode reactions for the reduction, but it tends to be water that ends up being reduced. And then you have this overall reaction that you see there and a general potential of negative 2.186 volts. So again, this is non-spontaneous without some outside source of energy. And so here's what here's also looking at electrolytic plating. So if you have jewelry or silverware, something that maybe is plated, so there's like gold-plated jewelry, silver-plated, sometimes jewelry, but often more like silver-plated silverware. This is the process using an electrolytic cell. So you have some energy, and then you're able to plate onto your cathode, which would be, for instance, maybe that's a copper spoon, and then you plate it with silver. So it's kind of cool stuff. Now we do have some quantitative aspects to this. So now we're going to get back into the math, but it's pretty easy math. The electrical current is defined as the rate of flow for any charged species. So this whole chapter, we've been talking about the flow of electrons. We measure current in amperes, and 1 ampere is equal to 1 coulomb per second. So the amount of charge transferred, Q, by the passage of a constant current, I, over a specified time interval, T, is given as Q equals IT. It's kind of like quit, but please don't quit. You're almost there. So the stoichiometry of a redox reaction can be used to derive the total charge that's involved. So you have your balanced reaction, and you see, okay, in this reaction, there's N electrons being transferred. So that means, okay, there's N electrons being transferred. So the actual amount of charge being transferred, sorry, my pen's being weird, that Q for the charge transferred is equal to N for the amount of electrons transferred times F, which is Faraday's constant that we talked about earlier, which is equal to 96,485 coulombs per mole of electrons. So some other units for Faraday's constant. That's the same thing. So let's look at an example of converting current to moles of electrons. We're told in one process used for electroplating silver, a current of 10.23 amps was passed through an electrolytic cell for exactly 1 hour. How many moles of electrons passed through the cell, and what mass of silver was deposited at the cathode from the silver nitrate solution? So we can use Faraday's constant to convert the charge into moles of electrons. So we first need to figure out the charge, though. So we need the charge, though, in terms of coulombs. And a couple things that we're told is we had 10.23 amps. So that is a coulomb per second. So we have 10.23 coulombs for every 1 second. And what we're going to do is go ahead and change this. Where was I? Look at our units here. And we're told that this was done for 1 hour. So we know that we have, actually I'm going to rewrite this. Instead of starting with the 10.23, I'm going to start with 1 hour. So we have 1 hour, and we know that there are 60 minutes for every 1 hour. And then we have 60 seconds for every 1 minute. So now we've changed to seconds, and then we know that we have 10.23 coulombs for every 1 second. So then this tells us that there were 36,830 coulombs. And so then N, well actually, if we go back, we know that Q equals N times F. So then N is equal to Q divided by F. So that is 36,830 coulombs divided by Faraday's constant, 96,485 coulombs per mole of electrons. So then this gives us 0.3817 moles of electrons that are transferred. So we're also told that we used a silver nitrate solution. So we also know that the cathode, the silver nitrate gives us Ag+, and that needs 1 electron to give us solid silver. Since we're plating silver, we're putting silver on it, so that means we're making solid silver. So we're starting from aqueous silver. Since we have silver nitrate, that's AgNO3, which means that the silver has a charge of +1. So this is going to solid silver. That means we have 1 electron that is being, or 1 mole of electrons being transferred for each mole of silver. So then our mass of silver, then we know we have 0.3817 moles of electrons. And we can use this balanced half reaction to know that we make 1 mole of silver for every 1 mole of electrons. And then we now have moles of silver. We need grams of silver since we want mass of silver. So that means we have 107.9 grams of silver for every 1 mole of it. And this then calculates out to be 41.19 grams of silver that was plated. So hopefully it's not too bad. And one last example. We're told in an application a 0.010 millimeter layer of chromium must be deposited on a part with a total surface area of 3.3 square meters from a solution containing chromium-3 ions. How long would it take to deposit the layer of chromium if the current was 33.46 amps? And we're told the density of the chromium is 7.19 grams per cubic centimeter. So the first thing we should do is get the volume of the chromium that has to be produced. So volume is going to equals length times width times height, and you could take this length times width, that's your surface area, multiply that times your height to get your volume. So then our volume, we have 0.010 millimeters times, we're going to make this into centimeters, we have 1 centimeter for every 10 millimeters. And so there's our height times our surface area, which it told us is 3.3 meters squared. And the reason we're turning this into centimeters is because our density is in terms of grams per cubic centimeter. So it's just to make our life easier. And then there's 10,000 square centimeters for every 1 square meter. And so this tells us that our total volume is equal to 33 cubic centimeters. So now we can use this volume to get our mass by using density. So there's 7.19 grams of chromium for every 1 cubic centimeter. So cubic centimeters cancel. And that gives us 237 grams of chromium. But when it comes to all of our equations for our coulombs and stuff, we need moles. So we can use now this grams to get our N, which is moles, using molar mass of chromium. And so there's 1 mole of chromium for every 52.00 grams. So this gives us 4.56 moles. And then we know that Q is equal to N times F. Okay. Oops, sorry. Yeah, Q is equal to N times F, but Q is also equal to I times T, which is the constant current over a time interval. But we're going to go ahead and start with the N times F. So the number of moles that are transferred here, we know we have 4.56 moles. But we also know from the reaction, when you look it up, that there are 3 moles of electrons that are transferred for every 1 mole of chromium. So that 4.56 moles we said, I misspoke, is the moles of chromium, not the moles of electrons. So you have to look up the half reaction as well for chromium. And we know it's chromium-3. So since it tells us chromium-3, that means we have to be transferring 3 moles of electrons for every 1 mole of chromium. You could find the half reaction and you would see that. So that gives us our moles of electrons times our Faraday's constant, which is 96,485 coulombs for every 1 mole of electrons. So we see all our units here even cancel. And this gives us 1.32 times 10 to the 6 coulombs. And then we know also that Q is equal to I times T, or that T is equal to Q over I. And Q, which we just solved for, is 1.32 times 10 to the 6 coulombs, divided by I, which is the current, and we're told that is 33.46 amps, which an ampere is equal to a coulomb per second. So we can see the coulombs cancel, and we get 3.95 times 10 to the 4th seconds, which we can convert to hours, and we get 11 hours. So 11 hours, but not bad, I guess. You just let it start going and then walk away and do your own thing, right? Okay, that does it for chapter 17. I hope this was at least a fun chapter for you guys. And I hope you're all doing well. And as usual, if you need any help, let me know.